Download this code from codegive.com, link in the description below. Welding thin versus thick metal, a comprehensive guide, with code considerations. Welding thin and thick metals requires distinct techniques and considerations due to fundamental differences in heat dissipation, material behavior, and potential defects. Using the wrong technique for the metal thickness can lead to disastrous results, including burn-through, warping, lack of fusion, and ultimately, a compromised weld. This comprehensive guide will walk you through the nuances of welding thin versus thick metal, covering crucial aspects like understanding the key differences, heat dissipation, distortion, and weld pool management. Choosing the right welding process, SMAW, GMAW, gtaw, and other processes. Preparation is paramount, edge preparation, cleaning, and fit up. Techniques for thin metal, pulsed welding, heat sinking, stitch welding, and specialized processes. Techniques for thick metal, multi-pass welding, preheating, joint design, and code considerations. Welding parameters, amperage, voltage, travel speed, gas selection, and wire feed speed. Preventing and addressing common issues, burn through, distortion, porosity, and undercut. Code considerations, specific requirements based on metal thickness and application, example AWS, ASME. Code examples, illustrating how code standards dictate material thicknesses and acceptable welding practices. 1. Understanding the key differences, The primary challenge in welding thin metal, typically considered anything 1/8 or 3.2 mm and under, is heat management. Thin metal heats up rapidly, making it susceptible to burn through and distortion. Thick metal, on the other hand, acts as a significant heat sink, requiring more heat input to achieve adequate penetration and fusion. Here's a breakdown. Feature: thin metal, thick metal. Heat dissipation rapid, localized heating slower, more widespread heating. Distortion high risk of warping and buckling, lower risk, but still possible with excess heat. Burn through high risk, requires precise control, lower risk, but can occur with excessive amps. Weld pool small, fast freezing, larger, slower freezing. Penetration requires minimal penetration to avoid burn through, requires sufficient penetration for joint strength. Cooling rate rapid, slow. 2. Choosing the right welding process, The choice of welding process significantly impacts the success of your weld. GTAW, gas tungsten arc welding / TIG, excellent for thin metals due to precise heat control. Also suitable for thick metal but can be time consuming. Offers clean welds and good control over the weld pool. GMAW, gas metal arc welding / MIG, versatile. Can be used for both thin and thick metals. Pulse welding, a GMAW variant, is particularly useful for thin metal. Faster than gtaw. SMAW, shielded metal arc welding / stick, less suitable for very thin metals due to its higher heat input. More appropriate for thicker sections. Requires more skill to avoid burn through on thin material. FCAW, flux cord arc welding, primarily used for thicker materials due to its high deposition rate. Laser welding, suitable for thin materials requiring high precision and minimal heat input. Resistance welding, spot welding, specifically designed for joining thin sheets. Process recommendation table. Metal thickness process recommendation notes. 1/16, 1.6 mm, gtaw, laser, resistance gtaw provides maximum control. Laser requires specialized equipment. Resistance is for overlapping sheets. 1/16, 1/8, 1.6 mm, 3.2 mm, gtaw, gmaw, pulse, gtaw still excellent, pulse gmaw can increase speed while maintaining control. 1/8, 1/4, 3.2 mm, 6.35 mm, gmaw, smaw, with care, gtaw gmaw is the most common. SMAW needs lower amp settings and smaller electrodes. gtaw for high-quality welds. 1/4, 6.35 mm, SMAW, gmaw, FCAW, SMAW and gmaw are workhorses. FCAW for high deposition rates and out-of-position welding. 3. Preparation is paramount ****. Proper preparation is critical, regardless of metal thickness. Cleaning remove all mill scale, rust, paint, oil, and grease. Use a wire brush, grinder, or chemical cleaner. Contaminants can cause porosity and weaken the weld. Edge preparation for thick metal, beveled edges are often required to create a groove for multiple weld passes. Thin metal usually only needs square edges, but ensuring they are clean and aligned is vital. Fit up accurate fit up minimizes gaps and stress concentrations. Use clamps, jigs, or tacks to hold the pieces in place. Large gaps require more filler metal and increase the risk of distortion and lack of fusion. For thin metal, tight fit up is crucial to prevent burn through. 4. Techniques for thin metal ****. Pulsed welding, GMAWP, gtawp delivers cycles of high and low current, reducing the average heat input. This allows the weld pool to solidify slightly between pulses, minimizing burn through. Heat sinking * use copper bars or blocks as heat sinks to draw heat away from the weld zone. This helps to prevent overheating and distortion. Stitch welding * instead of a continuous weld, make short, intermittent welds, stitches. Allow each stitch to cool before making the next, minimizing heat buildup. Skip welding * similar to stitch welding, but the stitches are placed further apart and in a staggered pattern. This helps distribute heat more evenly. Backstepping * start the weld slightly ahead of the desired point and weld backwards towards the starting point. This preheats the joint slightly and can improve penetration. Proper electrode angle * keep the electrode angle low to prevent overheating and burn through. Fast travel speed * a faster travel speed reduces the amount of heat applied to a specific area. Example, stitch welding code *. 5. Techniques for thick metal ***. Multi-pass welding * thick metal typically requires multiple weld passes to fill the joint. Each pass should be allowed to cool slightly before the next pass is applied. Preheating preheating the metal before welding reduces the temperature gradient and can prevent cracking, especially in high carbon or alloy steels. Consult material specifications for recommended preheat temperatures. Joint design proper joint design is crucial for achieving adequate penetration and fusion in thick metal. Beveled edges create a groove that allows for better weld deposition. Common joint types include V-groove, U-groove, and J-groove. Backing using a backing material, example copper, steel, supports the weld pool and prevents it from sagging through the joint. This is particularly important for single-sided welds on thick metal. Weaving a weaving technique, moving the electrode side to side across the joint, helps distribute heat and fill the groove. Example, preheating procedure, pseudocode. 6. Welding parameters ***. Parameter thin metal thick metal. ****. Amperage low, to prevent burn through, higher, to achieve adequate penetration. Voltage lower, to reduce heat input, higher, to increase arc length and penetration. Travel speed faster, to prevent overheating, slower, to allow for proper fusion. Wire feed speed, gmaw, lower, to match low amperage, higher, to match higher amperage. Gas shielding argon or argon-helium mixtures are common. CO2 or argon CO2 mixtures are often used. Electrode size, smaw, smaller, to concentrate heat and reduce current, larger, to handle higher amperage. 7. Preventing and addressing common issues ****. Burn through, thin metal reduce amperage, increase travel speed, use pulsed welding, heat sinks, or stitch welding. Distortion, thin metal use clamping, heat sinks, stitch welding, skip welding, or controlled cooling. Lack of fusion, thick metal increase amperage, slow down travel speed, improve edge preparation, or use a weaving technique. Porosity clean the metal thoroughly, ensure proper gas shielding, and use a low hydrogen electrode, SMAW. Undercut reduce amperage, improve electrode angle, or use a weaving technique. Cracking, thick metal preheating, proper joint design, and using a compatible filler metal can prevent cracking. 8. Code considerations ***. Welding codes are crucial for ensuring structural integrity and safety, especially in critical applications like pressure vessels, bridges, and buildings. Codes dictate material requirements, welding procedures, and inspection standards. AWS, American Welding Society, a widely used code for structural welding, pipe welding, and other applications. AWS codes specify requirements for welding processes, filler metals, welder qualification, and inspection. ASME, American Society of Mechanical Engineers, primarily focuses on pressure vessels, boilers, and piping. ASME codes are very strict and require rigorous testing and documentation. API, American Petroleum Institute, covers welding in the petroleum industry, including pipelines and storage tanks. General code implications based on metal thickness thin metal codes might emphasize minimizing heat affected zone, has, and distortion. Non-destructive testing, NDT, like visual inspection and dye penetrant testing, may be sufficient. Thick metal codes will focus on achieving complete penetration, preventing cracking, and ensuring adequate strength. More stringent NDT methods like ultrasonic testing, UT, or radiographic testing, RT, are often required to inspect the entire weld volume. 9. Code examples Let's consider a simplified example illustrating how a code might address material thickness. Hypothetical code requirement, based on AWSD 1.1, simplified. Scenario welding structural steel plates using SMAW. Code clause 3.3.2. Minimum material thickness for fillet welds. The minimum material thickness of the thinner part joined by a fillet weld shall be as follows. For fillet weld size up to 1/4, 6.4 mm, minimum material thickness shall be equal to or greater than the fillet weld size. For fillet weld size exceeding 1/4, 6.4 mm minimum material thickness shall be at least 1/4, 6.4 mm. Code interpretation asterisk. This clause means that if you are welding two plates together with a fillet weld, a weld joining two surfaces at approximately a 90-degree angle, and the fillet weld size is 1/4 or smaller, the thinner of the two plates must be at least as thick as the weld itself. If you use a fillet weld that exceeds 1/4, the minimum thickness of the thinner plate can't be less than 1/4. Code example implementation in C, simplified validation. Explanation asterisk. 1. Validate fillet weld thickness function asterisk. Asterisk takes the fillet weld size and thinner plate thickness as input, in inches. Asterisk defines a constant minimum thickness threshold representing 1/4 inch, 0.25. Asterisk implements the code logic from the hypothetical AWSD 1.1 clause. Asterisk if the fillet weld size is less than or equal to 1/4 inch, it checks if the thinner plate thickness is greater than or equal to the fillet weld size. Asterisk if the fillet weld size is greater than 1/4 inch, it checks if the thinner plate thickness is greater than or equal to 1/4 inch. Asterisk returns true if the conditions are met, the weld is valid according to this simplified code, and false otherwise. 2. Main function asterisk. Asterisk provides several example scenarios with different fillet weld size and thinner plate thickness values. Asterisk calls the validate fillet weld thickness function for each scenario. Asterisk prints the results to the console, indicating whether the weld is valid or not based on the code validation. Important considerations for code compliance asterisk. Asterisk refer to the specific code asterisk. This is a highly simplified example. Always consult the relevant welding code, AWS, ASME, API, N, etc., for the specific requirements applicable to your application, material, and welding process. Asterisk filler metal selection asterisk codes often specify the permissible filler metals based on the base metal and welding process. Asterisk welder qualification asterisk welding codes typically require welders to be qualified to perform the specific welding procedure. Qualification involves passing a test weld that demonstrates the welder's ability to produce sound welds. Asterisk procedure qualification asterisk complex welding procedures often require procedure qualification to demonstrate that the procedure will produce welds that meet the code requirements. Asterisk non-destructive testing, NDT codes specify the types and extent of NDT that must be performed to verify the quality of the welds. Asterisk documentation asterisk maintaining accurate welding records is essential for code compliance. This includes details about the welding procedure, filler metal used, welder qualification, and NDT results. Conclusion asterisk. Mastering the art of welding thin versus thick metal involves understanding the unique challenges presented by each material thickness. By carefully selecting the appropriate welding process, employing the correct techniques, and adhering to relevant welding codes, you can achieve strong, reliable, and safe welds. Remember that continuous learning and practice are key to becoming a proficient welder. Always prioritize safety and consult with experienced professionals when in doubt.